Okay, so these are called exponential functions because x is in the exponent. In the past, we've always had like y equals x squared, x cubed, but now x is in the exponent spot. So let's look what this graph looks like. This is the parent graph. I want you to memorize this. And so let's derive it this first time. So let's just plug in a few values out for x. 0, 1, 2, 3. Okay, so if I plug in 0, this would be 2 to the 0 power. If you remember, it's been a long break. But 2 to the 0 power is 1, so 0, 1 is actually the main point of this graph. It's the only point I need you to memorize on this parent graph. 0, 1 is the point I need you to memorize. The behavior I need you to memorize as well. So this would be 2 to the 1, which is 2. So you see the y value has doubled here. That's the way this works. 2 to the second power, when x is 2, would be 4, so 2, 4 is the point. The y value has doubled again. 2 to the third power would be 8. So the y value doubled again. If I kept going, it would be 4 to the 16th, 5 to the 32nd, etc. This graph's going up very quickly. In the past, parabolas only got a kind of a slower go up, but here it's really cooking up there. It's really moving up there fast. See what happened was when x is negative. So 2 to the negative 1 is 1 over 2 to the first, or 1/2. So negative 1, 1/2. So we're right in there. 2 to the negative 2 would be 1 over 2 squared, or 1/4. So let's have to do exactly somewhere in that neighborhood. 2 to the negative 3 would be 1 over 8, or 1 over 2 cubed. So 1/8. Getting smaller and smaller. You can probably tell because we dealt with these before. It's approaching asymptote there at y equals 0. So I do expect you to have this graph here, this asymptote labeled at y equals 0. This point here at 0, 1 labeled, the behavior of the graph is correct. That's a great sketch of the graph. You don't need to hit all those points. Let me talk about just how x, if you change that base of a there, what happens to this graph. So this is 2 to the x. Watch carefully. 3 to the x looks very similar. Let's go back to 2. There's 2 to the x. Here's 3 to the x. The only difference in the graph is really, it just went up a little bit faster, right? Same thing with 4 to the x. Looks almost like 2 to the x. 5 to the x, 6 to the x. Behavior of that graph's the same. It goes to that same point at 0, 1 in every case. So really changing that value doesn't make a difference. So if I said sketch the graph of y equals 3 to the x, y equals 3 to the x, sketch that graph for me. I would sketch it pretty much like y equals 2 to the x. It's going to have a point at 0, 1. Move up. Have an asymptote there at y equals 0. And if I asked you to compare, well, what is y equals 4 to the x, for example? Same basic graph. The only difference would be it's going to go up a little bit faster, right? So I don't expect you to get every point on those graphs correct for a sketch. Just get the basic idea here. So when we start with these graphs like 3 to the x, let's start by graphing the parent graph in every case here. So the parent graph of that is just, crosses 0, 1, has an asymptote at y equals 0, and the graph behavior looks something like that. So now let's talk about transformations. So the equation for this is y equals, let me use b here for that number in front just because we tend to use a for the base. A to the power of x minus h, that's in the exponent spot, plus k. So the k value that moves it up and down is out here on the outside, plus 2 in this case. So plus 2 is going to move this graph up 2 units. So if you take this point and move it up 2 units, there you are at the point 0, 3. The asymptote was at y equals 0. Now it's going to be at y equals 2. And the graph is going to approach on the left and go up really quickly after that point. There's your basic sketch of 3 to the x plus 2. If I graph 4 to the x, again, it's going to look just like 2 to the x pretty much. It's going to have this point at 0, 1, and it's going to have an asymptote here at y equals 0. So now be careful in this one. X minus h is kind of like in the parentheses. We've dealt with that before with circles, with parabolas. X minus h, because of that minus sign, this plus 2 is not going to move it to the right. It's actually going to move it to the left in this case. So every point gets moved over 2 units. So this point now is at -2, 1. And the asymptote, really moving a horizontal asymptote to the left, doesn't change it. It's still at y equals 0. But the graph will approach the asymptote on the left, hit that point, and move up pretty quickly. That's your basic sketch of that graph. So this is 4 to the x, and then we'll do the transformation here. So it goes through this point at 0, 1. And putting a 2 in front of it does change. So that's one of the few things. That will change the y-intercept. Notice like this y-intercept is always 0, 1. When you're multiplying all the y values, so we were at 0, 1, the y values by 2. So that's what this number does. So the new y value would be 2. So 0, 2. So it really hits it right here. What's interesting is, yes, the point does go through 0, 2, but the behavior of the graph over here, doesn't really change that whole lot. So it's going to still approach the asymptote on the left. The asymptote doesn't move up. The only thing that changes the asymptote is moving the k value, right? Moving it up or down. In this case, we're just stretching the point. This is called a vertical stretch. So the y values have been stretched, but there's still going to be an asymptote here. It's very important you know this one at y equals 0. So it's still going to approach the asymptote on the left. It's just going to go through a point a little higher up there, twice as big a y value for the y-intercept, and then move up. Let's look at a few more points here. So you probably have a good guess. Let's start with 2 to the x. Again, that parent graph looks kind of like this. Goes to the point 0, 1. It has an asymptote, horizontal asymptote at y equals 0. So just like before, when you have a negative in front of the function, this is going to be reflecting over the x-axis. So this point reflects over this x-axis. It's now going to be at 0, -1. And the behavior of the graph approaches the asymptote on the left, hits the point, moves down pretty quickly, something like that. All these transformations work the same way. So again, start with 3 to the x, and start with that parent graph. Looks like this. Goes to the point 0, 1, has an asymptote at y equals 0. So when you have the negative attached to the x, not in front of the function, that reflects over the x-axis. This is going to reflect over the y-axis. So you take all these points and reflect over the y. This part of the graph is going to reflect over to here. This part of the graph where it's approaching 0 is going to approach over here. It's going to approach the asymptote. So your graph looks something like that. Starts high. This is called exponential decay. This is exponential growth. You might hear about those terms in science class. And this is doing a little bit of both here. So if you start with the parent graph, and of course y equals 0 on the axis there is the horizontal asymptote. You're doing two things. So this is reflecting over the x-axis. It's going to reflect down to 0, 1, 0, -1. And then this one is reflecting over the y-axis. So it takes this graph, reflects over the y. So it's going to start low. Oops. Start low and kind of come up to this asymptote right here and approach the asymptote at y equals 0. So it still has an asymptote at y equals 0. That didn't change. It starts low and then approaches the asymptote on the right. There's another parent graph you need to know. So this is your second parent graph. Let's just plug in a few points here. And this is when x is between 0, a is between 0 and 1. I'm considering the negative value, just that's doing a reflection. So let's just talk about the value of a, whether it be a negative in front or not. I'd rather just talk about a being the number in here. So let's plug a few values in. So 1/2 to the 0, 1/2 to the 0 power. Well, anything to the 0 power is 1. So guess what? What's interesting, that point is the same on this parent graph. It still goes through the point 0, 1. You have to know and memorize that one point. Let's plug in first power. So this would be 1/2 to the first power, which is 1/2. So 1, 1/2. That's kind of getting smaller there. 1/2 squared would be 1 over 2 squared, which is 4. So 1/4. So it's getting smaller here. This ends up being 1/2 to the third power, which is 1/8. It's getting even smaller. You can probably tell it's approaching the asymptote there at, so draw there, y equals 0 is the asymptote. And then here at -1, this would be 1/2 to the power of -1, which is the reciprocal of that, right? That's what that negative exponent does, so it ends up being 2, so -1, 2, so it actually gets bigger there, the y value. This is 1/2 to the -2 power, so it's being put to reciprocal power, so this is 2 over 1 to the second, or in other words, 4. So -2, 4. And this is 1/2 to the -3. So if I flip it first, that's what the negative does, reciprocal. So it'd be 2 to the third power, which is 8. So -3, 8. It's like that. -4, 16, etc. So this is called exponential decay. Starts high and then approaches the asymptote on the right of y equals 0. So really what that, if you think about it, the reason this works, and that's kind of a different way of writing this, I could write this as 2 to the -x. Right? That's actually the same thing as 1/2 to the x. What's that do? That's a transformation over the y-axis. If you look at the original parent graph, what's it doing? It's reflecting over the y-axis. So it just took the original parent function, reflected over the y-axis. I think it's easier just to think of this, just go, okay, oh, this is exponential decay when it's to a fractional power there. So that would be the easiest way, just to memorize that one, kind of know that one. So this, again, is just transforming. So we're starting with the parent graph. It goes through 0, 1. This is going to move it down 3 units. So 1, 2, 3 units. So this is now 0, -2. And the asymptote is going to move down 3 units. So it actually moves down to y equals -3. And so on the right, it's approaching the asymptote. On the left, it's going up really quickly. There's a pretty good graph of your function. So 1/2 to the x minus 2, this one is moving it to the right. So it's taking that parent graph, which in this case is exponential decay, right? That's 0, 1. And moving everything to the right 2 units. So that point would now be at 2, 1. It's going to decay, so it's doing this, going through that point. I missed that point, but it's going through that point and approaching the asymptote at y equals 0. And this one, again, it's stretching it. So if you start with the parent graph, it goes through 0, 1. So it's interesting here. A lot of students think this is going to move it up 3 units. It doesn't move it up. It just stretches the y value. So that point, the point was at 0, 1. And now the point is going to be not at 0, 1. This is multiplied by the y value, so that would be 0, 3. So it actually only moved it up 2. It stretched the y value by a factor of 3. And so again, it's going to go through that point. It's going to approach the asymptote at y equals 0. It's going to go up really fast or decay really fast coming from the left. And so all these transformations work in a very similar way here as you go through here. So you start with the parent graph of exponential decay. There's 2 transformations happening here. So this is going to be reflection over the x-axis. So it's going to do kind of this number. And this is going to now move everything up 1 unit. So that point moves up 1. There's now the asymptote is at y equals 1.